projects. In this video, we are going to explain about the project, which is classification of diabetic retinopathy disease levels by extracting topological features using graph neural networks. Introduction of the project. Diabetic retinopathy is a leading cause of premature blindness in diabetic patients worldwide. Early diagnosis and timely intervention through fundus screening are crucial in preventing vision loss caused by retinal disorders associated with elevated blood glucose levels. Detecting diabetic maculopathy, a complication of diabetic retinopathy, requires significant manual effort from ophthalmologists. To enhance the analysis of retinal images, the project aims to leverage image processing methods, specifically computer assisted diagnostic systems. Traditional machine learning and deep learning methods have shown promise in automatically grading diabetic retinopathy and diabetic maculopathy. However, challenges such as the need for extensive data, domain knowledge for feature engineering, and optimization for clinical adaptations persist. The project introduces a hybrid graph convolutional network that combines DenseNet and graph convolutional network. This hybrid approach aims to improve the accuracy of diagnosing retinal disorders by integrating discriminative features learned through GCN layers. The project addresses the gap in retinal image classification using graph neural networks. The proposed HGCN incorporates both by integrating DenseNet and GCN. This innovative approach aims to enhance the interpretability and effectiveness of diagnosing diabetic retinopathy, providing a comprehensive solution for early detection and treatment. Objective of the project. The objective of the project is to develop a deep learning methodology based on graph convolutional neural network, which is GCNN, for the automated diagnosis of diabetic retinopathy, aiming to improve the accuracy and efficiency of disease severity level detection in fundus images. The aim is to implement a novel approach by integrating DenseNet effectively, extract essential features from retinal images, addressing the challenge of retaining high quality information encountered in traditional convolutional neural networks. The focus is on utilizing the GCNN component to identify and leverage underlying topological correlations within retinal images. This step is crucial for enhancing the understanding of disease patterns and severity levels. The aim is to compare the results obtained from the proposed GCNN based methodology with those of other state of the art techniques in the field. The aim is to demonstrate superior performance and validate the potential of the novel approach in advancing automated diabetic retinopathy diagnosis. The goal is to build multiple deep learning models including DenseNet 121, GCNN, and ensemble of DenseNet and GCNN. The objective is to evaluate and compare the performance of these models in diagnostic diabetic retinopathy. To implement this project, we need software and hardware requirements. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. And the hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. To implement the project, we have designed various steps in the flow of work. The first step is importing the packages. This step involves importing necessary libraries and packages that are required for the project. We imported TensorFlow and Keras for deep learning, Pandas for data manipulation, NumPy for numerical operations, Flask and SQLite for web application, and Seaborn and Matplotlib for visualization. Exploring the dataset. Here we have loaded DRD dataset, which is diabetic retinopathy dataset, and IPAX dataset. In this step, we explore the datasets, we understand their structure, size, and content. Exploratory data analysis include visualizing sample images, checking label distributions, and ensuring data integrity. The next step is image processing. Here, image augmentation is performed using image data generated from Keras. This involves several transformations, which are rescaling the image, which is adjusting image pixel values to a standardized scale. Shear transformation is changing the shape of the image by shifting pixels. Zooming the image is modifying the image size by zooming in or out. Horizontal flip is flipping the image horizontally, and reshaping is adjusting dimensions of the image which are required. Coming to building the model architecture is constructed in this step. It involves building an architecture such as DenseNet, model layers, activation functions, and other parameters are defined to capture and learn features from the input images. Training the model. The constructed model is trained using the pre-processed dataset. This involves feeding the augmented images through the network, adjusting the model's parameters during the training process to minimize the difference between predicted and actual outcomes. This step aims to make the model capable of accurately predicting diabetic retinopathy severity levels. Coming to the next step, which is Flask framework with SQLite for sign up and sign in. Flask, a web framework for Python, is utilized in conjunction with SQLite for user authentication. This step involves setting up a user sign up and sign in functionalities, ensuring a secure and controlled access to image analysis tool. The next step is user upload an image for analysis. User can upload retinal images through the web interface. This step involves creating an input mechanism for users to submit image for analysis. Coming to the next step, which is given input is pre-processed. The input image is uploaded by the users, which undergoes pre-processing steps similar to those applied during the dataset pre-processing. This ensures that image is in suitable format for the models to analyze. The next step is trained model is used for prediction. The pre-processed image is fed into the trained machine learning model and model predicts the severity level of the diabetic retinopathy based on learned features. The model uses its knowledge gained during the training to make an informed prediction. The last step is final outcome is displayed. The result of the prediction is displayed to the user. This includes information on the severity level of the diabetic retinopathy in the uploaded image. The user interface communicates the model's findings in a clear and user-friendly manner. Algorithms which are used in the project are DenseNet 121. DenseNet is densely connected convolutional networks. It is a convolutional neural network architecture characterized by dense connectivity between layers. In Dense 121, the number 121 indicates the total number of layers in the network, including convolutional, pooling, and fully connected layers. It is employed in the project for its efficient feature extraction capabilities. Dense connectivity enhances information flow through the network, allowing the model to capture intricate patterns and relationships in the retinal images. It is well suited for image classification tasks, making it a suitable choice for diagnosing diabetic retinopathy based images. Coming to GCNN, which is Graph Convolutional Neural Network. GCNN is a type of neural network designed to operate on graph structured data, where the relationship between data points are modeled as edges in a graph. GCNNs extend traditional convolutional neural networks to handle non Euclidean data, making them suitable for tasks involving structured relationships. GCNN is specifically tailored for the analysis of retinal images, where the underlying structure can be represented as a graph. By leveraging topological correlations in the data, GCNN aims to enhance the understanding of disease patterns and severity levels in diabetic retinopathy. It complements traditional CNNs by incorporating graph based information into the learning process. Coming to the next algorithm, which is DenseNet with the combination of GCNN, it is an ensemble learning involves combining multiple models to improve overall performance. In this case, the ensemble consists of both DenseNet and GCNN models, each contributing to the final prediction. The combination of predictions from the different models can enhance robustness and accuracy. The ensemble of DenseNet and GCNN is employed to leverage the strengths of both architectures. While DenseNet excels in feature extraction from the images, GCNN focus on capturing graph-based relationships. The ensemble model aims to provide a more comprehensive understanding of the retinal images, potentially improving the diagnostic accuracy of diabetic retinopathy. As an extension, we further enhance the performance by exploring other techniques of deep learning. Also, as an extension, we built the front end using Flash framework for user testing with user authentication. We have used accuracy, precision, recall, and FN score, which are the performance metrics, to evaluate this project. So, here we have the performance comparison graphs for all the models built in the project on the dataset, which is DRD dataset. This is accuracy comparison graph where x-axis represents accuracy score for each algorithm and y-axis represents algorithm names. Similarly, we will have for other graphs also. So first we will know what is accuracy score. Accuracy is the measure of the overall correctness of the model. It calculates the ratio of correctly predicted instances to the total number of instances. This is precision score comparison graph. It is the ratio of correctly predicted positive observations to the total predicted positives. It evaluates the accuracy of positive predictions. This is recall score comparison graph. It is also known as sensitivity or true positive rate. Recall measures the ability of the model to capture all relevant instances. It is the ratio of correctly predicted positive observations to the total actual positives. This is FN score comparison graph. F1 score is the harmonic mean of precision and recall. It provides a balance between precision and recall, especially when there is an imbalance in the class distribution. Here we have performance comparison graphs for all the models built in the project on the dataset which is IPACS. Here we have recall and F1 score comparison graphs for all the models built on the dataset which is IPACS. To execute the project, first we need to open the code folder which contains source code files. This is the code folder of the project. This is the DRD dataset folder in which we have different classes and we use all the datasets for training the algorithms. Here we have IPACS dataset in which we have different classes and we use all those classes for training the algorithm. This is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. And these two are the model files, which contain the algorithm information and that will be loaded into the project code during runtime. These two are the IPYNB files. These are the Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. This is the signup file. This file is the database file used to store the user information. Now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. By this, current directory will change to the code folder's path. So here we can observe that current directory is changed to the code folder's path. And here we need to type the command python space app.py. And now we need to click on enter. This will compile app.py file and it will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework follows the application locally at the default address, which is the localhost and the port unless configured differently. This is the localhost and this 5000 is the port. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project, which is displayed in the browser. And this web page is built by using the Flask framework. Here we can see a sign up link. First, we need to click on that and enter all the user registration details if you are signing up newly. I have already signed up and have an account in it. So we will directly click on sign in. Here we need to provide our credentials, which are the username and the password. So I'm giving my username and the password. Now we need to click on login. We have logged in successfully and we are redirected to prediction page. Now we will do the prediction for both the datasets which are IPACS dataset and DRD dataset. So first we will do the prediction for IPACS dataset. For that, under classification, click on IPACS link. Here we can see a choose file button. We need to click on that for uploading retinal images. So I'm clicking on choose file button. These are the IPACS dataset images. So from the folder, I'm selecting the first image. Now click on open and now click on upload. Here, based on the uploaded retinal image, we got the prediction as moderate diabetic retinopathy, which means that the person is suffering from diabetic retinopathy, but is at moderate level. Now click on try again to upload the other image. Click on choose file. I'm selecting this image, which is the third image. Click on open. Here we can see that image has been loaded. Now we need to click on upload. Based on the uploaded image, we got the prediction as no diabetic retinopathy, which means the person is not having diabetic retinopathy. Click on try again. Click on choose file. This time we will upload this image. Click on open. And now we need to click on upload. Here we got the prediction as proliferate diabetic retinopathy. Now we will upload one more image. Click on try again. Click on choose file. I'm uploading the last image. Click on open and now click on upload. So here we got the prediction as the person is suffering from diabetic retinopathy and he is at severe diabetic retinopathy level. Now we will do the prediction using other dataset, which is DRD dataset. For that, under classification, click on DRD. Here click on choose file. Now we will upload images from the DRD dataset folder. For that, click on back arrow. I'm opening DRD dataset folder. I'm selecting the first image. Click on open and now click on upload. Here we got the prediction as no diabetic retinopathy, which means based on the uploaded image, the application is judging that the patient is not having diabetic retinopathy disease. Now click on try again to upload the other image. Click on choose file. This time we will select this image. Click on open and now click on upload. So here we got the prediction as moderate diabetic retinopathy, which means person is having diabetic retinopathy but he is at moderate level. Click on try again to upload other image. Click on choose file. This time we will select this image. Click on open and now click on upload. So here we got the prediction as proliferate diabetic retinopathy, which means the person is having diabetic retinopathy disease but he is at proliferation stage. Click on try again. Now we will upload one more image, so click on choose file. This time I'm selecting this image, click on open and now click on upload. Here we got the prediction as severe diabetic retinopathy, which means person is having diabetic retinopathy disease but is at severe level. Now click on try again. Click on choose file. This time we will upload this image, click on open and now click on upload. Here we got the prediction as the person is suffering from diabetic retinopathy disease and he is at proliferation stage. Now click on sign out. In this way, if we upload the retinal images to the system, then the system will detect whether the person is having diabetic retinopathy disease or not. If he is having, it will detect it as which stage it is. Conclusion of the project. The project successfully implements a deep learning methodology incorporating DenseNet 121 and GCNN to enhance the automated diagnosis of diabetic retinopathy. The use of dense connectivity in DenseNet 121 and the exploitation of topological correlations in GCNN contribute to more accurate and efficient disease severity level detection. The project conducts with a notable achievement in advancing automated diagnostics for diabetic retinopathy, particularly through the strategic combination of DenseNet 121 and graph convolutional neural network algorithms. This ensemble model excels in disease severity level detection, surpassing the state-of-the-art techniques. The integration of the Flask framework with SQLite for user sign-up and sign-in, coupled with a user-friendly web interface, enhances the accessibility of the developed diagnostic tool. Users can conveniently upload images and the system provides clear outcomes, facilitating practical applications in clinical settings. The automated diagnostic tool developed in the project directly benefits patients with diabetes by enabling early and accurate detection of the diabetic retinopathy. Additionally, healthcare professionals can gain a valuable resource for efficient diagnosis, allowing for timely interventions and improved management of diabetic eye complications.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.